Hello everyone, welcome to our differential equation class. In this video we are going to talk about a particular type of matrices called diagonalizable matrices. These are matrices that they are simple enough so we can do many calculations with these matrices, and complicated enough that they appear in many physical situations. We are going to start our video introducing a particular type of matrices, of diagonalizable matrices, that is called diagonal matrices. Then we are going to introduce the diagonalizable matrices, and we are going to end the video with a very interesting connection between the diagonalizable matrices and the eigenvalues and eigenvectors of those matrices. So that's the plan for today. Let's start introducing a simple type of matrices called diagonal matrices. And these are matrices that have the following form. An n times n matrix D is called diagonal if and only if it has this form. So we have non-zero coefficients in what we call the diagonal of the matrix. Recall this is a square matrix, the same number of rows as columns. So we have a diagonal of elements, and this can be arbitrary numbers, but anything outside this diagonal is 0. So we have 0 everywhere outside the diagonal. We are going to use the following notation for diagonal matrices. Since we don't want to write so many zeros, we are going to write a big 0 on the upper corner and a big 0 on the lower corner, and then coefficients only in the diagonal. Or even better, we are going to use this notation, diagonal, and then we are going to write only the important coefficients, which are the coefficients in the diagonal of the matrix. A typical example, the simplest example of a diagonal matrix, is the identity matrix, which is a diagonal matrix that has all the coefficients in the diagonal equal to 1. So, for example, an identity matrix is the matrix diagonal that has 1 all on the diagonal, or another way to write it is 1 in the diagonal and a big 0 here and a big 0 there. For example, in the 2 by 2 case, the identity 2 by 2 is nothing more than 1, 0, 0, 1. A diagonal matrix that has 1 in the diagonal. Well, a diagonal matrix is a more general type of matrices where we allow any value on the diagonal. So why we are interested in this type of matrices? Well, because they are very simple matrices. In particular, matrix multiplication is actually commutative for diagonal matrices. That is, if you have one diagonal matrix and another diagonal matrix and you multiply, this is the same as switching the order of the matrices. This is not true in general for any matrices, but it is true for diagonal matrices. That makes calculations very simple to do with diagonal matrices. An example of a calculation that could be in general complicated but is very simple with diagonal matrices is compute powers of a diagonal matrix. These are very simple to compute. Let's see how this is done. Compute the power n arbitrary, n any positive integer, for this matrix. This is a diagonal matrix with 3 and 2 in the diagonal. Okay, so let's do the calculation solution here. Let's start. What about if we want to compute the power n for arbitrary n? So let's start with d square. What is d square? Well, it's the product of the matrix times itself, which in this case, so is d times d. And we know what the matrix is. It's the matrix 3, 0, 0, 2 multiplied by itself, 3, 0, 0, 2. And this is the matrix product, is this coefficients times this coefficient. You see the 3 with the 3 and the 0 with the 0. So we end up with the 3 squared and nothing else. Then this coefficient times this coefficient, the 0 is going to kill the 3, and the 2 is going to be killed by this other 0. So we still get 0 here. Something similar happens here. 0 kills that number, 0 kills this number. So this is 0. And then this coefficient gets the zeros together and the 2 together. So we have 2 squared. So very easy to see that we get the square of each diagonal element. And now if we go to power 3, d cubed, then this is going to be d squared times d. But we already have d squared, which is diagonal again. D squared 3, 0, 0, 2 squared multiplied by 3, 0, 0, 2. And obviously the same calculation tells us this is 3 cubed, 0, 0, 2 cubed. And this is the calculation we need to do. In general, if you now start doing this calculation many times, then you're going to end up with the calculation d to the power n, which you can always write it as d to the power n minus 1 times d. And then you're going to see that the d to the power n minus 1 is going to be 3 to the power n minus 1, 0, 0, 2 to the power n minus 1. And this has to be multiplied by one more matrix d. That here it is. And then we are going to end up with 3 to the power n, 0, 0, 2 to the power n. This is essentially what we say a proof by induction. So we assume the formula works for n minus 1, and we show that it also works for n. And that's it. That is going to say, therefore, the formula is, when the metric is diagonal, is d to the power n is going to be 3 to the power n, 0, 0, 2 to the power n. And this is how we compute powers of a diagonal matrix. Now let's go over a little remark. In general, if you put any coefficients a and d instead of 3 and 2, this calculation we have done here is exactly the same. So we are going to end up with the result that the power n of this diagonal matrix is the power n of the diagonal elements for any diagonal elements. But it's not true that this would happen when the matrix is not diagonal. When you have coefficients here that they are different from 0, then this is not equal to the power n of each coefficient. The formula is way more complicated. The formula is simple only for diagonal matrices. Another thing that is very simple for diagonal matrices is computing the eigenvalues and eigenvectors of a diagonal matrix. The eigenpairs of a diagonal matrix d1, dn are simply the eigenvalues are the diagonal elements, and the eigenvectors are the vectors 1 and 0s, where the 1 located in the place in different places that give you the corresponding eigenvalue. So for example, the first element in the diagonal has eigenvector 1 in the first position and then 0, 0. The last eigenvalue, so the last position in the diagonal, give you the eigenvector with the 1 in the last position. Something in the middle, the 3 is going to have 0, 0 in the third position, a 1, and then zeros all the way until the end. So position 3 has eigenvector in the position 3, a non-zero component. So and we can check that this is the case. It's very simple to check. For example, let's grab the first eigenvector. So we have our matrix. Our matrix here is D1 all the way up to the n, have zeros everywhere else, and then we multiply by the vector 1 and then 0 all the way up to the end. So when we do this product of this column with all these rows, these zeros are gonna kill everything that is here. They are gonna kill everything, and then it's only gonna survive the first column. And the first column has a one non-zero element in the first component and then 0 everywhere else, and this is what is going to be multiplied by 1. So we are going to end up with the 1, 0, and then zeros up to the end. And then we can pull common factor the d1, and then we obtain the vector 1, 0, 0, 0, 0. And there it is. This vector is an eigenvector, and this number is the eigenvalue. So this is lambda 1, and therefore this is v1. And you do the same calculation for the other vectors, and you're going to verify that these other vectors are eigenvectors and the diagonal elements are the eigenvalues. So every calculation is simple if the matrix is diagonal. The only problem is that diagonal matrices don't show up in many applications. What it does show up is a type of matrices a little bit more general called diagonalizable matrices. So let's introduce this type of more complicated matrices called diagonalizable matrices. And here is the definition. An n times n matrix A, so we are always working with square matrices, is diagonalizable if and only if there is an invertible matrix P and a diagonal matrix D, so that the original matrix A can be written as a product of three matrices, which are the matrix P, the diagonal matrix, and the inverse of the matrix P in that order. So we can factorize matrix A as a product of three matrices and the middle matrix is diagonal and the other two are inverse of each other. Then we say matrix A is diagonalizable. And why we say that matrix A is diagonalizable? Because then it's very simple to see that we can transform matrix A into diagonal matrix by a simple multiplication. So you see what happens when we multiply the whole equation by P inverse here and P inverse. That is going to give you an identity, and then you're going to have P inverse A. And on the other side we have P inverse. So if we multiply now this equation by P, here we are going to get an identity, and then we end up with the diagonal matrix. So it's very simple to transform matrix A into a diagonal matrix by this multiplication. And suppose you want to do a calculation with matrix A, and it's a complicated calculation, so you first transform the matrix A into a diagonal matrix, do your calculation with the diagonal matrix, which is usually simple, and at the end transform back with this type of product, and you get matrix A, the calculation with matrix A. So that is the idea behind this type of matrices. Diagonalizable matrices are matrices where calculations can be done in a simple way, and actually they have a lot of applications in the real world. A lot of physical systems can be described by diagonalizable matrices. So let's see an example of a diagonalizable matrix. And here it is. Our old friend, the matrix 1, 3, 3, 1, we say that is diagonalizable, and in order to verify that this is true, we need either P or P inverse or D. Well, here is P. With this matrix P, we can verify that matrix A is diagonalizable because we can use this formula here, which is equivalent to the diagonalizable condition. We can use this formula here on the right. So if we grab our matrix A and we multiply by P inverse and by P, which we have P and therefore we have P inverse, if we get something diagonal, then we have verified that matrix A is diagonalizable. So let's do that. So solution, let's do it here, solution. Let's verify that that matrix is diagonalizable. The first thing we need to do is we need to compute P inverse. What is P inverse? Well, it's 1 over the determinant of matrix P. The determinant is the product of these two components, 1 minus 1, so is 1 plus 1. So let's write it like this, minus 1. And then we need to switch the diagonal elements, which is nothing happens, and then switch the sign on the other coefficients, and here it is, 1/2, 1, negative 1, 1, 1. Or once we have this matrix P inverse, we can compute then the product of P inverse matrix A and P. What do we get? Well, P inverse is 1/2. Then we have 1, negative 1, 1, 1. Then we put our original matrix. The matrix is 1, 3, 3, 1. And then the original matrix P, which is 1, 1, negative 1, 1. We are claiming this is the right matrix P. And now we have to do a product of 3 matrices. The order, how we do the product is not important. This one first, and then the product of that, or this product first and then we product with that, is the same thing. The product is associative. So let's do the product of these two first. So we are gonna keep here matrix inverse, so 1/2. We are gonna have 1, negative 1, 1, 1. And now let's do the product of these two coefficients times that. We are gonna get 4. Here and that we are gonna get 4, so we get 4 and 4. And then this column with the first row, second column, first row, we are gonna get 3 minus 1, so we are gonna get 2. And then here we are gonna get negative 3 plus 1, so we are gonna get negative 2. So that is what we get so far. And now, well, now maybe it's a good idea to actually simplify the 1/2 with the whole matrix, because this matrix has multiple by 2 in all the components. So maybe now is a good time to simplify to avoid bigger numbers. And then we are going to end up with 2, 2, 1, negative 1. Okay, now it's a good idea to do the calculation. Here we get 2 plus 2 is going to be 4. Recall, we need to get a diagonal matrix if A is diagonalizable. Then this product, we are going to get 0. That looks good. And then this product, we are going to get 1 minus 1, 0 again. So that's it. It's diagonalizable. And the last product is negative 1, so negative 2. Well, it doesn't matter what diagonal matrix is. The important thing that this is a diagonal matrix. So yes, this matrix A is actually diagonalizable with that matrix P and this matrix D. Before we continue, let's highlight something that is going to become very important pretty soon. Recall, what we have here is matrix A is the matrix 1, 3, 3, 1. We found out that the diagonal matrix is 4, negative 2, and matrix P is matrix with these coefficients. Okay, but now let's recall something that we already know about matrix A. We have computed before the eigenvalues, 4 and corresponding eigenvector, and the other eigenvalue of this matrix is negative 2 with eigenvectors negative 1, 1. And now notice something. This is quite interesting. This eigenvalue here, 4, is what shows up in the diagonal matrix, and one could see that one could think it's a coincidence, but the other eigenvalue also shows. So both eigenvalues show in the diagonal matrix. That is interesting. And notice that the corresponding eigenvector for the first eigenvalue is right here in matrix P. And the other eigenvalue also shows in matrix P, is the other column. So this is very interesting. And could that be a coincidence only for this matrix? It is very a strange coincidence. Well, actually, this property is what this calculation suggests is actually true in general. And this is our next result. And here it is. Our next result is the connection between the diagonalizable matrix and its eigenpairs. And here is the result. Suppose we have a matrix A that is a 2 by 2 matrix and has eigenpairs of this form: lambda 1 v1, like for example here, and lambda 2 v2, like for example here. And suppose one important condition: the two eigenvectors are not proportional to each other, just like here. Here we have the eigenvector, if we draw the plane, R2, the first eigenvector is the eigenvector 1, 1, so something like this. And the other eigenvector is something like that, v2. So obviously here v1 is not proportional to v2. To be proportional means that the two eigenvectors are on the same line, and they are clearly not on the same line, so we satisfy this assumption. Well, if we have that, then this is equivalent. So this happens if and only if matrix A is actually diagonalizable, and then matrix D, the diagonal matrix, has the eigenvalues in the diagonal, and matrix P has the eigenvectors in the same order. If you have lambda 1 in the first component of the diagonal matrix, V1 has to be in the same column, in the first column of the matrix P, because they are a pair, and the other pair on the second part of the two matrices. We are going to prove that this is the case, that this is an if and only if. And to prove that result, this theorem for 2 by 2 matrices, we need a previous result that is important, which is a relation between this condition on vectors and a property of this matrix P. And the relation is this: if you have any two vectors, v1 and v2, just arbitrary vectors, then the vectors are going to be not proportional to each other if and only if the determinant of the matrix that has these vectors as columns is different from 0. So not proportional, different from 0, this is equivalent. So to see that this result is reasonable, suppose we have two vectors, v1 not proportional to v2, suppose, then, well, we can do a picture of these two vectors, and if the picture I draw is very similar picture to this one. So not proportional means they are pointing in different directions in space, or in the plane in this case, because these are 2 by 2 vectors. Two vectors. So vector with two components. So these are vectors that they are not proportional to each other. Well, because they point in different directions, they form a parallelogram, and this parallelogram has area different from 0. But we have seen that the area, this area here, is actually the absolute value of the determinant of a very particular matrix given by these vectors as columns of the matrix. So the absolute value of that determinant is the area, and because they are pointing in different directions, we see that this is equivalent to say that the determinant of this matrix V1, V2, where these are vectors, is different from 0. So we see clearly in the picture that this is a geometrical proof that this condition is equivalent, the vectors not proportional to each other is equivalent to the determinant of that matrix being different from 0. But we can do the proof also analytically. So we can call this remark the geometrical proof. And now let's introduce the analytical proof, which sometimes people are more comfortable with. So let's start introducing our hypothesis. We know that V1 is not proportional to V2. Okay. And in this analytical proof, it has several parts, but we are going to go only on one part because it's simpler. And this is the part where all the components of the vectors, the 4 components of the 2 vectors, are all non-zero. All components non-zero. It's easy this way. If a vector has a component 0, then you have to consider the proof for this case in a separate way, and it's easier and it's easy to do. So the complicated part of the proof is when all the components are non-zero. Let's suppose that. So this is equivalent to say that now let's write down in components, and let's use different colors for the different components of the vectors just to keep track of the vectors. This is the vector 1, so vector 1, component 1, and vector and component 2 of vector 1. This is going to be our vector V1, and let's use green for the vector 2, which is going to have component 1 of vector 2 and component 2 of vector 2. So with this notation, the condition that we just said, well, this condition here is equivalent to 2 equations, one for the first component, one for the second component, and the equation is that V11 is not proportional to V12, and at the same time let's put it down here, V21 is not equal with the same constant C to V22. Here the constant C is the same in both equations. If you have only one equation, of course there's always exists the constant C, and then this happens, but then here, but the C's are different. So what we are saying here is that the same constant C cannot be in both equations. Well, all that, of course, is equivalent to, since we are in the case that all the components are different from 0, we can divide by V12, for example, and we can divide by V22, and then these two quotients are not going to be equal because this constant C cannot be equal here. So this condition is equivalent to say that V11 divided by the other component, which is the V12, has to be different from V21 over V22. We drop the V22 here, and this quotient has to be different from this quotient. Okay, but that's it. We are almost there. this is equivalent to say what happens if we multiply now by b22 and then by b11. We put this here and this coefficient here and this coefficient here, and then we are going to have v. Let's put it like this. Let's start with the red. v11 multiplied by v22 has to be different from v21 multiplied by the other, which is v12. So okay, so we can put everything on one side and we can say that let's go to the colors. v11 multiplied by v22 and then minus v21 multiplied by v12. This of course is different from 0, but this is also equal to the determinant of a matrix that has v11 here and v21, and over here v12 and v22. That determinant, you see, if we compute the determinant, we get this factor minus this factor, and this is exactly the determinant of the matrix. This is the same as the determinant of the matrix that has v1 as the first column and v2 as the second column. So that's the proof. Oh, let's go to blue to complete the proof. And yeah, it's kind of too cramped over here, so let's go a little bit higher up. And now, oops, we can put it there. So this is the analytical proof. And with the color, hopefully it's easier to track the different vectors. And yep, that's the proof. So the only thing that we need to do to complete the proof is what happens if one of these two coefficients are 0, and this is an easy case, you can work it out. But basically we have proven this result. And with that result, we can now go back and prove this result here. So now let's prove the theorem. And the theorem is an if and only if. So we have two things to do. Prove it in one way and then on the other way. So here is one way. This way here. So in this way, given the eigenvectors, so lambda 1 v1 satisfying this equation and lambda 2 v2 satisfying that equation, and recall these vectors are not proportional to each other, then in that case define these two matrices, and now we need to show that P inverse is actually A. We need to show that. And how we are going to do it? Well, we are going to start computing what is the matrix A multiplied by P. We don't have matrix A. The only thing we have is that lambdas and v's are eigenvectors, but the coefficients of A, we don't have them. So how we can do this product? Well, we can do this product using these properties, because this is just matrix A multiplying P, and P has the vector v1 as the first component and the vector v2 as the second component. And then this is going to be because of the matrix vector product, how it's defined. So because of the matrix multiplication is defined in terms of matrix vector products, this is just A v1, A acting on the second column v2. But here we can use the assumption that, well, the v's are eigenvectors, and then we are going to get something of the form lambda 1 v1 on the first column and lambda 2 v2 on the second column. Okay, we stop the calculation there, and now let's do this other calculation. What is matrix P acting on matrix T? This multiplication. Well, we have matrix P matrix P is V1, V2 as column vectors, and matrix D has lambda 1 in the first component, a 0, 0, and lambda 2. Recall these are 2 by 2 matrices. And the product here is this column times the first components on this row, and then this 0 is going to multiply this by 0 all the components on the second column, so it's going to be 0, and this lambda 1 is going to multiply, so what we are going to end up is multiplying this column by lambda 1 and this column by 0. So what is going to be the result? The result is going to be lambda 1 V1 in the first column. And if we do this multiplication here, we are going to end up multiplying 0 by the first column and lambda 2 by the second column. We do it all along the matrix, and the result is lambda 2 V2. And from here we see that we get the same result. So clearly we have proven that A multiplied by P is the same as P multiplied by D. Alright, but now we know that the other hypothesis we have is that V1 is not proportional to V2. Well, the lemma we have proven implies that the determinant of this matrix that has V1 and V2 as columns is different from 0, which is equivalent to say that determinant of P is different from 0. So therefore P is invertible. So P inverse exists. So we can multiply the whole equation by P inverse from the right, and we are going to obtain here an identity, and here is our result. Matrix A is diagonalizable with that P and that matrix D. So this is the proof in this direction. What about the proof in the other direction? Well, in the other direction, our hypotheses are that we have a matrix P given by these two columns, we have a matrix diagonal D given by these two components, and we know that P inverse exists, and that matrix A is given in this form. So now we need to show that this is an eigenvector and this is an eigenvalue of matrix A. This is an eigenvector, this is an eigenvalue of matrix A, and these two eigenvectors are not proportional to each other. That's what we need to do. Okay, so let's start with the equation that we have. That the equation we have is A is equal P the P inverse. So we multiply by P on both sides. So let's write A over here. Let's multiply by P on both sides. Here we are gonna obtain an identity. So we know that matrix A times P is equal matrix P times D. Alright, so we can compute matrix this product A times P, just like we did it before. Is matrix A acting on V1, V2, and just as we did before, this is A acting on V1 and A acting on V2. Okay, but we need to stop here now. We don't know what A acting on V1 is, but we still have the other product, the product P times D, which is the same as we did before, V1, V2, acting on the matrix with components lambda 1, lambda 2 in the diagonal, and 0 everywhere else. And we have seen that the result of that is lambda 1 V1 and lambda 2 v2. So now we are assuming that these two equations are the same, so therefore these two have to be the same. And from here we get that the matrix A acting on v1 has to be lambda 1 v1, and the matrix A acting on v2 has to be equal lambda 2 v2. So v1 and v2 are eigenpairs. And we also know that P inverse exists. So P inverse exists. That implies determinant of P is different from 0. That implies that the determinant of v1 and v2, these two column vectors, is different from 0, and the lemma says that therefore v1 is not proportional to v2, which is exactly what we wanted to prove. So this is how you prove. Here we can go a little bit higher. So again, it's not everything so cramped at the bottom. And now much better. And we have proven then this result. This is how you prove this result, which is the connection between a matrix being diagonalizable and their eigenvalues and eigenvectors for 2 by 2 matrices. One important remark about diagonalizable matrices is that the decomposition into factors of the diagonalizable matrix is not unique. So let's see that in an example. We already know that this matrix is diagonalizable, and we already know that this matrix has these eigenvectors. And now we already know the connection between this matrix and being diagonalizable and the eigenvalues and eigenvectors. For example, we have seen that if we introduce matrix D to be 4, 0, 0, negative 2, the eigenvalues, and the corresponding, and the matrix P with the corresponding eigenvectors 1, 1 and negative 1, 1, then we know that we have proven that matrix A can be written as P, the P inverse, and this matrix contains the eigenvalues and this contains the eigenvectors. But a similar decomposition is, let's say, we have a similar decomposition where we put the eigenvalues in different positions. We put here negative 2, 0, 0, and 4. This also is a matrix with the eigenvalues in the diagonal. And now if we put matrix P, let's call it D tilde, and matrix P tilde to be, well, now this is the first column here. So in the first column should be the corresponding eigenvector, so negative 1, 1, and in the second column the other eigenvector. But with that with those matrices, we still have the decomposition P tilde, D tilde, and then P tilde inverse. You see, it's not the position of the eigenvalues is not important as long as they are in the diagonal. And we have many options for eigenvectors. For fixed eigenvalues, we have many options. For example, we have a third decomposition here, which is, let's pick up the same matrix D tilde, negative 2, 0, 0, 4. But now, let's pick up different eigenvectors. This is going to be different. For example, in the first column, we put an eigenvector with eigenvalue negative 2, but something of the form 2, negative 2. This is an eigenvector that is proportional to that, so it's perfectly fine. And then here, I don't know, 7, 7. Well, that decomposition also gives you A as P double tilde the tilde p double tilde inverse. So there are many, infinity many decomposition of matrix A as a diagonal as these two factors. So a diagonalizable matrix can be written as a product of these three factors with the condition that we have the eigenvalues in the diagonal and the corresponding eigenvectors, but we have a lot of freedom in choosing the diagonal matrix and the invertible matrix. Now this theorem, now let's go back to the general theorem. The general theorem that we prove for 2 by 2 matrices actually can be proven for n times n matrices. And it looks something like this. An n times n matrix A, so a square matrix A, that has n eigenpairs, and here we have the first pair and the last pair, eigenvalue, eigenvector, eigenvalue, eigenvector. And now the condition that the vectors are not proportional to each other now is written as the vectors have to be linearly independent. We are going to see what that means. With that condition, this is equivalent to matrix A being diagonalizable with the matrix P containing all the eigenvectors, matrix D diagonal containing all the eigenvalues in the same order. What is this condition of the vectors being linearly independent? Well, let's go to 3 vectors. Then we can understand what do we mean by that. Suppose we have 3 vectors, so we are in the case of 3 by 3 matrices. And then we have 3 vectors, and we are going to say that these vectors are linearly independent if and only if none of this vector is a linear combination of the others. That's the condition. If one of the vectors is linear combination of the others, we say the vectors are linearly dependent. So what do we mean by none of the vector linear combination of the others? Well, here we have a few examples to try to understand that. These 3 vectors that they are mutually perpendicular, the vectors I, j, k, mutually perpendicular in R3. These are the vectors with component 1, 0, 0, 0, 1, 0, and 0, 0, 1. These are linear independent because neither of these vectors is combination of the other 2 because they are in different, they are all perpendicular. But what are vectors that they are linearly dependent? Well, when these 3 vectors belong to the same plane. For example, here, suppose we have one plane that contains all 3 vectors, like here. Then vector 3 obviously is linear combination of the other 2. But also vector 2 is combination of v1 and v3. And vector 1 is combination of v3 and v2. So each of the vectors is combination of the others. So we say they are linearly dependent. So another example of linear independent vector, they don't need to be mutually perpendicular. For example, we have two vectors that they are not proportional to each other, define a plane, and the only thing we need for the 3 vectors to be independent is that the third vector is not in that plane, like here. Then we are going to say the vectors are linearly independent. There could be another case of vectors linearly dependent when all 3 vectors align in the same direction. Then, well, this is another case of vector linearly dependent. So hopefully this clarifies a little bit what do we mean by linearly independent. The vectors point in 3 vectors, for example, have to point in 3 different directions in space. They span the whole vector space R3. Linearly dependent, they don't. They span a plane or a line. With that condition, we have this theorem, the generalization of the theorem we have proven for 2 by 2 matrices. And now, let's see examples. This example, what we are back to 2 by 2 matrices, which are our main interest in this video are 2 by 2 matrices. And in this example, we show that, matrix A is diagonalizable, but not every 2 by 2 matrix is diagonalizable, because here we have a 2 by 2 matrix that is not diagonalizable. And what happens, because we have this theorem here that gives us an if and only if, a matrix is diagonalizable if and only if the matrix has two eigenvectors not proportional to each other. If we have a matrix that is not diagonalizable, that means one of these conditions is not satisfied, and actually is this condition. So we have only one eigenpair, and we don't have this eigenpair for non-diagonalizable matrices. When a matrix is not diagonalizable, that doesn't exist, and therefore that doesn't exist. And this is the example below. So let's go pretty quick on that example. First, the diagonalizable matrix. Well, we already know this matrix is diagonalizable because it has these pairs, and these vectors are therefore v plus. We have seen is not proportional to v minus. We have seen that. So that means the vectors are linearly independent, matrix A is diagonalizable, and we have written what are the matrices. The matrices. Matrix A can be written as P, D, P inverse, and we already know matrix D is, for example, 4, 0, 0, negative 2, and for example, matrix P is, of course, 1, 1, negative 1, 1. Okay, we know that. What about this matrix here? Well, when we compute the eigenvalues and eigenvectors of that matrix, you're going to see that it has only one eigenvalue, and then all the eigenvectors are proportional to the vector 1, 0. So any other eigenvector has to be proportional to v0. That means any other eigenvector is proportional to v0. In that case, matrix B is not diagonalizable. There is no way we can find another eigenvector not proportional to the vector v0. So when that happens, we cannot do the decomposition P, D, P inverse. So, why we are interested in matrices that they are diagonalizable? We said because calculations are simple with diagonalizable matrices. And here is an example. We did an example with diagonal matrices, computing powers of diagonal matrices. And well, powers of diagonalizable matrices are also simple to compute. And this is our last example for this video. Show that when you have a diagonalizable matrix, then the products are easy to compute. You don't need to compute n products to compute a to the power n. You need to do 3. And the proof is similar to this result as the proof for diagonal matrices. Just compute what is a square first, and a square is going to be a times a, which is, because a is diagonalizable, is p, d, p inverse, and then p, d, P inverse, and of course these two matrices cancel into the identity, and then we get P D square, P inverse. And you see that this is going to happen over and over, because when we do a power 3, we get powers 2 times a. Power 2 we already computed, and then we have matrix A, which is P, D, P inverse, and again this product is going to cancel out into an identity, and again we are going to get P D cube P inverse. And if you keep doing this calculation over and over, you're going to end up with a to the power n, which is going to be a to the previous power times a. The previous power is going to have this formula d to the power n minus 1 P inverse, and here we are going to have the last power P D P inverse. Of course, this is going to give us again an identity, and then we are going to end up with P d to the power n p inverse, and that is more or less how we prove that result. So having this formula is quite useful because then we can compute an arbitrary power of any matrix that is diagonalizable, like this one here. And the only thing we need to do is use this formula. You see? And powers of a diagonal matrices are super simple. So suppose you want to compute our final example of this video, this power, an arbitrary power n of this matrix. So you don't do powers like this, 1, 3, 3, 1. Don't do that because that is going to be very complicated. What we do is you compute the eigenvalues and eigenvectors of this matrix. Here they are. You write the matrix A in the PD P inverse decomposition, and now we use that result. And now we use that A to the power n is going to be 1, 1, negative 1, 1. Then we are going to have, so this is the same as saying that A is P d P inverse, and that implies that the power n here is going to be P d to the power n P inverse, and this is what we are computing here, 4 to the power n 0, 0, negative 2 to the power n. And then here we have P inverse. So that is what we need to do to compute n powers of a matrix that is diagonalizable. Two matrix products. So we do it in any order. So for example, in this order, we keep the 1 and the 1, negative 1, 1. And then we still have the 1/2. And then we have 4 to the power n times 0, 4 to the power n. And then here we have what did I do? This column times this row is gonna give 4 to the power n. Okay, this column times this row is gonna give me something else. It's gonna give me negative 2 to the power n. All right, and then if we do that times that, we are gonna get 4 to the power n. And if we do that column, that row, we are gonna get negative 2 to the power n. Okay, now it's better. And then we need to do the last product, and we are gonna leave it as we get it. This is gonna be 1 is gonna multiply that coefficient, and negative 1 is gonna multiply that, so the negatives are gonna cancel out, and we are gonna have 4 to the power n plus negative 2 to the power n. This is gonna be our first component. Then the second component is gonna be 4 to the power n minus 4 to the power n minus negative 2 to the power n. Okay. Then this column, this row is gonna have a minus here, so we are gonna have 4 to the power n minus 2 to the power n. That is that component, and the very last one, this times that, is gonna be 4 plus 4 to the power n plus negative 2 to the power n. And this is the matrix. Of course, we can simplify a little bit more, but it's not worth it because we don't want to do any further calculations with this matrix, so we leave it as it is. But we have computed power n with an arbitrary n of a matrix that is diagonalizable. It's super easy to do. If the matrix is not diagonalizable, well, you need to do the products by hand of matrix by itself n times, and the formula is very complicated. Alright, so this is a good place to stop. See you guys in the next video.